Good afternoon again. So I'm going to continue off and do a different spin on autocorrelation compared to Martin Lindquist's talk. But first, so there's my slide isn't. Okay, so for some reason, the first slide isn't showing. So we'll move on to the second slide, which is what you were supposed to see is a reference to an old paper by Yule from 1926. It's called Why Do We Sometimes Get Nonsense Correlations Between Two Time Series? And so Yule was one of the first people to identify the problem of serial correlations and its impact on studying bivariate correlations. Roughly speaking, what he showed empirically was that exactly what Martin was alluding to earlier, which is if you have two time series that are just self-correlated but have no correlation between them, Yule showed empirically that you might see arbitrarily large correlations fluctuating between +1 and -1. But his was an empirical proof and was an empirical result, and recently some mathematicians actually proved that the standard deviation of an empirical bivariate correlation in this context will be 0.5, which basically means that we should expect, empirical bivariate correlations between two autocorrelated processes to be highly variable. Okay, and the perspective I'm coming from here is that actually, in the history of fMRI, in task fMRI, people have spent a lot of time thinking about how to deal with temporal and spatial autocorrelation, but we haven't fully been, until recently, we've sort of neglected the autocorrelation issues in functional connectivity, and that's something I want to spend a little bit time digging into today. Okay. Firstly, so what I want to do here is, I see. So my apologies. It looks like my slides are outdated. Like it's an older version that was supposed to be fixed, but hasn't been. And so forgive me for stumbling here. So what I want to discuss today is a broad and flexible class of spatiotemporal models that are capable of addressing serial correlations in our data. Okay, so roughly speaking here, fMRI Bowl time series consists of volumes or measurements. Those are the rows, and the columns are, say, brain regions or voxels. And there's a lot of dependence between all of these measurements. So there's covariance between every element of this matrix. And so spatiotemporal models are capable of modeling all the correlations in this kind of data. So, wow, okay, there's a lot of empty slides here. So what was supposed to be here is my objective for the talk, which is, I'll tell you the first, which is I want to show you, I'm going to deal with only constant, static functional connectivity models in this talk, but I want to talk about things that are not functional connectivity. PDF, yes, please do that. Okay, so they're going to switch to my PDF, which will hopefully, all right. Okay, so this is what you were supposed to see. All right. So I want to revisit the issue of serial correlations, but in the context of constant functional connectivity. And then I want to dig a little bit deeper into models of functional connectivity where functional connectivity is constant, but other components are time varying potentially, and how this might impact sliding window correlations and seemingly dynamic functional connectivity. Okay. So we already saw this. So broadly speaking, the class of spatiotemporal models for time series data can be quite big. Okay. And what I want to focus on today is a distinction between stationary models and separable models. And as you can see, this is hopefully gives you a perspective of the variety of approaches there can be. And the thing I want to highlight is that one can be, separable and not stationary, or stationary and non-separable, or can be both. And we'll dig into a little bit on what this actually means. So broadly speaking, when something is stationary, it means that the actual individual time points between, so for example, the correlation between two rows or the correlation between two columns in this data don't depend on their absolute location. They only depend on their lags. Okay, so this is the statistical definition of second-order stationarity. Okay. In contrast, there's the idea of separability, which says that the joint, covariance between every element of this matrix can be decomposed exactly into just a temporal covariance part, so the covariance between the rows, and a spatial covariance part, which is the correlation and the covariance between the columns. Okay? So these are separable models of separable spatiotemporal models. And a thing I'm going to come back to later on, so something you want to look at is, let's say we were to look at the covariance between two columns at one given row. Then in a separable kind of model, this means that the correlation between every two pairs of columns can actually vary as a function of time. So there is these kinds of models permit the variance of your data to vary with time. Okay, so that's a feature I'm going to highlight and come back to revisit later on. And one can also have in this context, and I think what's relevant to fMRI data, is the idea that we don't expect our spatial data, the correlations between, say, two brain regions of interest, to be stationary. They definitely don't just depend on the lag between them, on the distance between them. But it's possible, for example, to model the temporal dependence in a stationary way. But this class of models is very flexible. You can either be dependent in time in a stationary way or a non-stationary way. So that's the class of models I want to deal with today. Okay, so the typical model, implicit model of functional connectivity we usually work with are the idea that all our fMRI observations are IID Gaussian. And when we compute a Pearson linear correlation between two regions of interest or two voxels, we're implicitly assuming that this model holds. And what this model is implicitly assuming is that there is no dependence between the rows. But of course, we know this is not true. So just a little bit of notation here. So the spatial covariance, or the functional connectivity here, I denote by sigma, and the inverse correlation is, the inverse covariance is theta, which models, partial correlations and graphical models and conditional dependence. So for today's talk, it doesn't, I think you can roughly treat them as equivalent. I'm not going to dig too deeply into that, so they're both equivalent. So what I want to point out is that the standard multivariate Gaussian is like a special case of this more general class of distributions called matrix variate normals, and which is an instance of even more general class of like just matrix variate distributions. And what they help us do is to model more flexible forms of dependence. So to understand what this class of distributions does, so this is still the IID case. And what you're seeing here with that funny squiggle between the identity and the Kronecker product, what it basically means is that in the IID case, every time point has an identical covariance matrix. And that's what you're seeing here. Okay. But in the more general case, when there's actually dependence, so for example, right now what you're seeing is if you consider an AR1 model, it means that the past is the future. The future is dependent on the past, conditional on the present, right? So that kind of AR1 model captures that kind of dependence. And structurally, what this means is that the temporal dependence matrix, if you look at the inverse of the temporal covariance matrix, what you see is this kind of banding structure that you see in orange over there. And so there's a corresponding Kronecker product. Okay. And so the separability assumption basically takes what could have been a very complex and high-dimensional covariance structure and boils it down to something that's much more low-dimensional, and that's why it's a very nice class of models to work with. Okay. So I'm going to now give you a simulation, a sort of quasi-pseudo-real simulation to study why using these kinds of models is important. Okay, and so in red is a procedure that accounts for the serial correlation in the data based on the models I just, the Kronecker separable graphical models. And in blue, you're going to see a result that doesn't do any whitening at all. Okay? And what we're trying to do is I took an empirically derived network structure, and I used that to simulate data from this model. And we're going to see how well we recover the true functional connectivity in this context. Okay? And so what you're going to see is ROC curves with the true positive rate on the y-axis and the false positive rate on the x-axis. And the results look like this. So what you can see here is that accounting for the serial correlation in the data makes your estimates of functional connectivity far, far better. All right, we have very few false positives, and we recover functional connectivity where it is, and don't infer spurious functional connectivity where it isn't. And so this is an old idea, but I think it's the fact that we consider it somewhat controversial to do, and we don't do it often enough in functional connectivity, I think, is a problem. And I think this is one illustration of why this is important. And so just to expand this, we looked at this in a couple of different dimensionality scenarios. So the first, you can say where there's roughly more time points than there are ROIs. In the second case, there's roughly equal number of time points and equal number of ROIs, for instance. And in the third case, there's like fewer time points and a lot more ROIs. And you can see that as the networks get larger, it's really kind of critical and quite important to do this kind of whitening, or our estimates of functional connectivity are very, very noisy and very poor. So, so to summarize here, the class of models I introduced are able to model very flexible forms of serial dependence. So for example, you could have time-varying AR models, you could have time-varying moving average models, you can have combinations of them, and all of them can be modeled by these spatiotemporal models. And I think that's a huge advantage to us as we start looking at functional connectivity not just at rest, but also in the context of task, and the context of movie watching and naturalistic stimuli and so forth. So I think they're a very useful class of models, and the problem of serial correlation is going to, is going to be there no matter what kind of experimental design we work with and what scenario we look at functional connectivity. So, so that's the first half of my talk. Second half. So now I want to come back to Yule, and he pointed out something very interesting in his 1926 paper, which will look familiar to you because this is a problem that we've been rediscovering in the literature in the last few years. So what Yule did is he looked at two harmonic time series that had no noise whatsoever, so sines and cosines that have some offset. And if we were to look at the whole time series, we would not consider these two. These two time series are orthogonal. They have no correlation between them. And, but what he pointed out was that if you look at the instantaneous correlation between these two, it will seem like they are correlated, and it'll fluctuate back and forth between -1 and 1. So I highly recommend reading this paper because I think it was very prescient, and I think we're still grappling with the same sorts of problems that he identified in that paper. And I think some of the recent insights we've had regarding the problems of sliding windows is exactly captured by some of these examples. And the issue of, if you look at a too short a window length and you're not looking at the time series globally, then you're kind of missing the big picture, and you're going to see, it's going to seem like there's correlations when there are none. And so, inspired by that, I wanted to look at, are there cases now in these very flexible class of spatiotemporal models I just talked about, are there cases where functional connectivity is actually constant, but there's some other component of the time series that's changing? Is that also capable of producing spurious local correlations? Okay. So that's the question. And so in order to do this, I'm looking at a couple of different kinds of I'm going to consider a few different kinds of functional connectivity models. In all of them, functional connectivity is the parameter in green, and the parameter in green doesn't change in time at all. Okay? But in the first kind, I'm going to look at a simple class of VAR models, which I can explain further if we have questions or time. So in VAR models, the idea is you're very familiar with these because if you're used to fitting an AR model, for example, at every voxel, you're effectively fitting a VAR model. So in a VAR model, serial correlation is allowed to vary with every region, but the serial correlation is not allowed to change in time. Okay? But the fact that each time series has a different serial correlation parameter can potentially, hypothetically, we know that this biases bivariate correlations, and conceivably, I thought, is this potentially inducing spurious correlation? So that was one question. And in the second class of models, I'm going to look at two variations. One where serial correlation varies with time. So the little picture below it is where you see the kind of, at each time point, the dependency with other times looks different. So that's how the serial correlation is varying with time. And a different class where there is no serial correlation, but I'm letting the variance change with time. And so this is, you could think of this as a toy simplification. So Martin talked about the stochastic volatility models where they employ a more sophisticated form of time-varying variance. In this case, all it's saying is that the global variance at every time point is different. Global variance across all ROI. So it's a very simplistic kind of time-varying variance scenario. Okay. So let's look at the first case. So what I wanted to do was I created a simulation where our null hypothesis is that of constant functional connectivity set to some value, 0.3 in this particular bivariate simulation. Okay. And we employed a test statistic that's not based on sliding windows at all, but it's borrowed from the financial time series literature, where the financial time series literature cares a lot about looking at time-varying correlations, and so they have created a whole slew of test statistics to test the hypothesis of whether correlations are changing with time or not, that are not based on sliding window approaches. So that's the test statistic I used. And to create the null distribution, I used a wild bootstrap procedure. Okay. So when I looked at the VAR model, what happened was actually we don't see, according to if you use a proper test statistic to test whether or not correlations are constant or not, this test statistic works, and it did not reject the null as it should. So type 1 error was very well controlled in this situation. The second scenario, which is where the serial correlations are allowed to vary with time, and I did a similar approach, and again, the situation is that we're able to control type 1 error, so we're not rejecting the null hypothesis in this scenario, as we should. So this is good news. But in the context of time-varying variance, this is a case where the type 1 error was not controlled at all. And this is a case where if you don't incorporate in your model the fact that the variance can potentially be changing with time, then we're seeing these spurious, it looks like dynamic, we are rejecting the constant correlation scenario. So this is very, so this is my analysis of let's look at constant functional connectivity, but let's look at our other kind of time-varying parameters capable of inducing spurious correlations. And so, so the main message here is, yes, accounting for serial correlation is definitely important because the actual values of the correlations we infer is made better once we whiten the data and account for serial correlations. But in the context of time-varying functional connectivity, the good news is that, at least for the naive, so I've not looked at all possible metrics here. I've only looked at the idea of can we reject the constant correlation hypothesis where the constant correlation is not null, it's not zero. And the good news there is the serial correlations don't seem to be creating a problem there. But there is a nuisance parameter, and that's the variance, or it may be a nuisance parameter, it may not be. If you heard Eugene Duff's talk or have read some of his previous papers, I think there's a couple of people in addition to Martin Lindquist, who care about looking at signal variability in the brain. So maybe signal variability has some neurophysiological basis, or maybe it's partly nuisance. But regardless, if we don't model time-varying variance, it's potentially going to seem like we have time-varying functional connectivity. Okay, so that's the core of my message for today. But for the discussion later on, I do want to foster a discussion here with my colleagues on, how do we think, how should we validate, and how should we go about validating whether or not dynamic functional connectivity exists. And so I sort of have a proposal here, which maybe we can discuss later on during the discussion, which is maybe, can there be some kind of hierarchy of model testing where we go from simple to more complex time-varying models? And the idea being, we need to make sure the simpler parameters, like the first-order parameters, like the spatial mean, like the mean of our data, like the variance in our data. So unless, we need to detect, is there a time-varying component to the mean? And if there is, then we should model that, and then move on to the next one, which is a second order, which is variance, and look for whether there's time-varying variance. And if there is, then we should be modeling that too. And then and only then can we move on to the correlations. And once we're at the spatiotemporal correlations, well, it's not clear that, should the temporal correlations or the functional connectivity get precedence? So there is no clear hierarchy or ordering there. But so that's kind of an open question, what should be given preference there. But if your goal is to study functional connectivity, then the temporal correlation is kind of a nuisance. On the other hand, if you're actually interested in studying the dynamics in the temporal domain, then actually functional connectivity is kind of your nuisance. And so it might be that depending on what you're studying, you need to account for one or the other appropriately. But that's sort of the idea I wanted to throw out there. And for my colleague Zhao, who is going to talk about in the next talk on empirical validations, maybe there's a similar idea we can propose, which is that not only should we be looking at sliding window sorts of correlations in other modalities and in animals and so forth, but maybe there's all these other parameters we should be studying in those contexts as well. So that's sort of my question to my colleagues for later on. All right, thank you.